Okay, so this is the, okay, I think I have a bit of time, so let me briefly explain what the Weinbergs mentioned now. Very briefly, to motivate us to continue to learn QFT2. I think we should, so what he mentioned, 3-to-1 theory. Okay. So, and from here you get the 8 photon, so which is called gluon, and from here you get the 3 photons, and from here 1 photons. In total, you have a 12 photons. That's what he mentioned. And then here, this is G and G prime, depends on and GS, coupling constant. And this one is called electro weak theory. And this one is called quantum chromodynamics, and which called QCD. And then what he mentioned that the G and G prime and its so-called angle, which is often written like a theta W. Often people call Weinberg angle, but according to Weinberg, this W means weak. From here, you can get the so-called coupling constant weak. Okay, mass of W plus minus and Z. Oh, okay. So W plus minus Z is really here. This 3 is W plus minus Z, and this is called gluon. And from mass of W plus minus Z, and then also it's determined that yeah, I mean, of course it's anyway. This is imprecise. Okay, a bit imprecise. Of course, theta determine mass, but anyway, and also electric charge E. And then, so the mass, since the gauge imbalance does not allow the usual Yamil theory or gauge boson to have a mass, but according to the Weinberg, it's a spontaneous symmetry breaking, which is taking the Higgs field takes this kind of form, phi. So the phi is a scalar field, as you learn, and potential of this form. And since the minimum of this theory, so I'll just give you a motivation. Minimum of this potential is here rather than 0. Therefore, there is some so-called quadratic potential around here. So this will give you mass of the W and Z. So this is called spontaneous symmetry breaking. And also, so he mentioned the renormalizability that so when we learn scalar theory, now it takes the following form: phi minus m squared phi squared plus lambda factorial phi to the fourth. So this is the phi-4 theory we have learned, and of course you can just put some other phi cube term as you learn in homework. Coupling constant, let's say lambda semi of 3 factorial. This is allowed interaction term, and this has this has mass square. This has dimension is 2, dimension is 0, dimension is 1. Mass dimension is 0 and 2 and 1, as you can see. As you recall, the Lagrangian density is the d4x L, and this should be dimensional. And this is the inverse of the mass. So mass to the 4, inverse mass to the 4. So L should have the mass to the 4, which means that this is mass dimension 1 because 1 over x in 1 and 1. So therefore, phi should have mass dimension 1. So 1 plus 1 plus 1 plus 1 means 4, which means that this guy has a mass dimension 2. So therefore, this should have mass dimension 2. As you can easily see, m squared really give you the mass dimension 2. So therefore, here, mass dimension 1, the mass dimension 0 for 5 to the 4. But on the other hand, if you add the reason why I play the Weinberg video is to explain this one. If you add a 5 to the 5th term, let's call lambda mu rho, maybe rho to the 5 to the factorial term. So this has mass dimension -1. And this is not renormalizable term. If you include this one at the UV Lagrangian and started to go to the UV Lagrangian, so this coupling constant ceases to zero. If you go to the IR. In any case, if you start with this Lagrangian and then start and it goes to the IR, this term does not affect anything because of the dimensionality. So this is not renormalizable term. Anyway, so that's what Weinberg mentioned about this renormalizability. So therefore, the reason why we do not consider the lots of like complicated interaction term, whatever phi to the n term, because the renormalizability just requires to think only up to here, not the higher ordered interaction. So that's the beauty of renormalizability. Of the anyway. So that's anyway. Some additional explanation to Weinberg speech, and hopefully you can learn many things in QFT2, and hope many people. Anyway, you already suffer a lot in QFT1, so it's not so difficult to continue QFT2. Okay, so let me continue to. Unfortunately, I stopped recording in the middle, so today you see the 2 video. Anyway, I'm very sorry for this organizing. So big homework if you submit on by hand, and then Tencent side, if you want to pick homework, you should come to Jiangwon campus 123, office 123, and number 2. And then today, homework 6 is due date is today. And we are planning to grade it within a few days, hopefully by Friday, and send a solution 6 to on Friday, so that you can just review homework 6. And if you have a question, you can ask in the office hour or WeChat whenever. So because we only have a 1 week till the end, till the date of final exam. So feel free to ask questions. And as I mentioned, the final exam. Okay, let's talk about final exam. So it's online, unfortunately, and you should turn on the camera on. And you cannot type on the laptop, so you cannot type, so that hopefully you won't. Anyway, so you should open all the reference. You can of course see the reference on the laptop, so you can just only click on the, or like a scroll the reference on the PDF file, whatever, on the laptop, but you cannot type it. So typing means if I allow you to type, you can search internet or like communicate. So you're not allowed to do that. So switch off the WeChat, and also don't use the phone, but you can use the whatever iPad to read or whatever. Anyway, so I don't care so much about the final exam, so but it's mandatory to do that. So anyway, it's like a limited time of homework or whatever. So the first problem is various small problem, like as I mentioned, especially you have to be careful about the critical algebra and some like a small bunch, 4 small problem. And the problem 2 is tree level amplitude. And number 3 is loop evaluation, one loop evaluation. So these are the content of final exam. So anyway, so you already did it. These are anyway in the homework, so you're already familiar with. You just need to do the somehow limited time. I don't know why, but that's what the university asked me to do. But anyway, so don't worry about the final exam so much. So just review homework a little bit, and then that's enough. Don't be so scared by final exam. Any question about the final exam? It's just one camera is enough. One camera is enough on the laptop. I don't care. And please do not type. Please do not type. I mean, anyway, so try not to cheat. I mean, if one camera, it's easy. Okay, I like to. Okay, just go restroom before the exam. I mean, if you want to cheat, I mean, everywhere you can do that actually, indeed, and online. I mean, just put the lots of whatever devices, and then just hide the camera. Anyways, cheating cannot be avoided. I mean, with one camera or any camera. But anyway, so I don't care so much about the. So just go to restroom before the exam, and then don't escape to the somewhere, something like that. Anyway. And if you want to try to cheat, it's easy to cheat. So, but I cannot avoid it. Anyway, so that any other question about the final from how about Tencent side? Okay, then let's continue about this story in that case. So where are we? So we are define A in and move on to this. Okay, I will erase. Okay. So now, so we continue the LSC. Okay, 40 minutes, enough time. So we define a diagram in this way, not define, derived, so that so this P1, so this S matrix element, what was it? Over there is the P1 out, and the Q1 in is indeed given by minus limit t goes to minus infinity I times z on half t d cubed x1 and e to the minus I q1 x1, and then derivative, and this is we're looking derivative and p1 out, and now we insert phi of x1 and then q2 in. So that's what we have. So here phi of x times z z inverse 1/2 will determine phi in. That's the definition of phi in here. And then so and also what we did is that the phi in and then this this operator up to normalization. I'm not careful about normalization here, but this will create the A in dagger Q1. So therefore, this will create acting on the here, you get the Q1. So therefore, I just omit Q1 here. So it starts with Q2. It starts with Q2. Okay, maybe it's better to write the bigger. Sorry. I think I will write them bigger downstairs. Minus limit t goes to minus infinity I times z minus 1/2 dqx1 minus iq1 x1 derivative of real derivative p1 pn out and phi of x1. It starts with q2 qr. So that's what we have. So this operator with this combination will create a in dagger, so that acts on this state that will create Q1. And then so you can do the same trick for Q out. And in fact, so one can just use the following trick that the limit t goes to infinity minus limit t goes to minus infinity hopefully you can see. Okay. D cube x1 f of x1. I mean, just you can do the integral for parts. Fortunately, yeah. Anyway, so this is the integral parts. You can add the time integral dt and partial t dq x f of x1 and then t initial tf and ti goes to infinity minus infinity tf goes to infinity. So if you do the and t integral like this way, and then you get this limit t goes to infinity, limit t goes to minus infinity, and that is indeed equal to d4 integral of f of x1. Okay. Let's say, so you just do the this, you apply this one to the above setting, and what we have is that the so this P1 out Q1 in is indeed equal to square root to EQ 1 P1. Oh my goodness, I think I should explain A out dagger Q1 Q1. I will explain what it means just a moment. And plus I z minus 1/2 d4 x1 minus q p1 not out Q2. Okay, so that's what we get. So the reason why I got this one is that in fact, so minus limit t goes to infinity is equal to t goes to infinity minus t goes to infinity plus this one. That's what you mean. So, which means that this one corresponding to this guy, and then orange. Hopefully, Tencent can distinguish this guy. Orange in the red is this guy, and of course, this guy corresponding to this guy. Okay. So as you recall, the t goes to infinity. If you go to t goes to infinity, did I write somewhere in? Yeah. So t goes to infinity of phi of x is indeed z inverse t1 half phi in. So phi out. Sorry, phi out of x is essentially limit t goes to infinity of phi of x. Okay, as you recall. So when if phi goes to future infinity, it becomes the phi out. And if phi out, if you plug that one into here, phi out, it's the same thing. Phi out and phi out. So therefore, if you use this t goes to infinity part, instead of phi in, it becomes phi out. So therefore, one can extract the creation operator of phi out state. That's what it means. So from this red, so this the dotted part is a combination of the limit t goes to infinity times minus sign plus this guy. Okay. So therefore, and this red guy will, if you do this red guy, you get the A out. That because of this relation. Okay. You understand? Is it okay? And then this orange one will give you this one, just usual. So this f of x is this guy, entire this guy, okay? Entire this guy. F of x is okay. Let me write down the. Unfortunately, I hope you can. I found my phone. I was looking for my phone. So this one, this guy, blue guy, I hope the Tencent can. This is f of x1. And just plug into here and just apply phi of 0. I think it's imprecise. Maybe I have to get rid of integral. This is the f of x. Then this orange part becomes here, and red part, because of this relation, it creates A out. And now, if you look at the first term, A out really acts on here by annihilation operator. Okay, so I forgot. This is called bra, right? And this is called cat. And for when you take from cat to bra, so where's F? Yeah, here over there. If you take a Hermitian conjugate, A dagger is A, right? Just A dagger means A. So therefore, this A dagger acts on here as annihilation operator. Okay, because this is bra state. So therefore, this will give you something like so this red state will give you square root 2EQ 1 delta PK minus Q1 and P1 dot PK cut out, and then P2. This hat means get rid of. Get rid of. So this means that this. Where should I erase? The first one is the disconnected. So you have an I. So this means that so you have a Q1, Q2, QR, and you have a P, P1, Pn is equal to Q1 and Pk, and then you have like this one, Q2, QR, and then P1, Pn, but the Pk is left. Pk, Pk is get rid of without Pk. So this delta function is essentially the Q1 just become Pk. So which means that there's no interaction Q1 to Pk. Q1 should be equal to Pk. There's no interaction, and the other particle interacting each other. It's just push out here into here. And this delta function is there's no interaction, one particle, there's no interaction, just go to from past infinity to future infinity. You understand? Is it okay? So this A out means acts on here as an annihilation operator means that oh my goodness, you should point me out, this should be Q2. So that's the first meaning of first term, and second term, we just manipulate a little bit more. So this means, and then what I need to do is bit more precise to be a bit more precise. D3 and 2 pi and Q here, and the sum of. So this is the first term. So K can be anything. K can be any 1 to n. So can be L1 to n. And plus, plus the really interaction. Anyway, that's what I mean. Here is Q1. I mean, this is QR, P1. So the first term is just one particle do not interact from past infinity to the future infinity. And let's look at the second term. Second term is equal to. We just need to do the manipulation. Just derivative of this guy and this guy. That's it. And I think I should call it this x1. X1. The second term is the d for x1. And the good thing is that now you have a Lorentz invariant measure, and then also shows your square, and e to the I q1 x1 and dot here is just this inner product, and then plus e to the I q1 minus q1 x1 and the partial del 0 square and the inner product. So this is the the derivative, and then of course cross term cancel each other because of sign. Did I? Okay, so here's the relative sign minus sign here. So therefore, once you act, so now it's a 0, right? 0 and 0 and 0. The cross term is this del 0. Del 0 acts on F here and G here. Then they cancel, right? the cross term cancel. Do you understand? So this dou 0 can act on F and also G, right? But they cancel each other because of this relative sign. So therefore, what's left is the dou 0 square and del 0 F square here. That's what's written here. Okay. Now, so we can use the fact that the this is just free field propagator. So therefore, what we can use is that the del 0 square minus the nabla. I'm sorry, I think plus nabla square plus n square is equal to acts on e to the minus I q1 dot x1 should be equal to 0. So this is the definition of the I think did I make a mistake? Yeah, here minus sign. Sorry, minus sign. Sorry, minus sign. Then so if you apply this one, this is equal to d4 x1 and then nabla nabla m square x on e to e. I mean, here of course this is really like a here. Minus iq1 dot x1. Of course there's a overall bracket here and dot 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 dot. And plus this side is the same as before. Just do that, and then you can do the integral by parts. And then this, so you just do the integral parts of this spatial integral, and what's left is that just bring it to here. You get this guy acts on. So therefore, this is equal to e4 x1 e to the minus I q1 x1, and then usual Klein-Gordon operator acts on this inner part by integral parts. From here, so this spatial derivative acts on this guy, but by integral parts, this spatial integral can act on this inner product parts. That C this guy. That C this guy. So therefore, at the end of the day, second term is just the inverse Fourier transformation of this Klein-Gordon operator acts on this inner product. That's what happened. I think if you be careful, so if you are careful, you have to multiply I to the z over there is minus 1/2, minus 1/2, and this I times z minus 1/2. I times t minus 1. Okay, so this is the second term of this. Okay, so this is, as I recall, the first time is disconnected one. So this is called disconnect diagram. So this is called disconnected. And this is connected. And we can play the same game. You can do the same game for all states. For instance, let's see. So you can do the same game for our state. For instance, this P1 out, and the Q1 in can be written as the okay. Let's consider only connected one. Connected. Maybe. Okay. Let me do a bit. Okay, so this is a disconnected one. And plus, you can do the same thing for here. Plus I, the inverse, 1/2, and the fourth y1, e to the I p1 y1, and then Klein-Gordon operator acts on. You can do the same exercise. Acts on, actually here p2, pn out, and q1, qr in. You can do the same game for all states. So here out means essentially you just, instead of minus, you get the plus sign. And here you have to be careful about sign here. So here you have a minus iq1 x1. On the other hand, you have a plus ip1 y1. Because of this is the future infinity. So therefore, one has to be careful about sign of the Fourier mode of the yeah. Anyway, so detail I will omit. So you have the difference between the A in acts on cat and then A out acts on the bra. So the difference only appear in here. Because I mean here it's a dagger, right? Here A dagger acts on right, but here A out, there's no dagger. Acts on P1 acts on the bra. So therefore, the difference is really coming from only the sign here. Acts on here. Okay. So at the end of the day, so what we have, so this Klein-Gordon operator acts on this correlation function or inner product, and then you can do the same game for everything. So at the end of the day, so what we have, we can play this game. And at the end of the day, erase this part. At the end of the day, so what we have is this is equal to sum of this connected diagram. Plus I z minus 1/2 and plus r, and then dy1 total dyn dx first integral 1 dot dxr to the fourth, and then times e to the I. It's just write down lots of stuff. x1 plus pn xn minus q1 x1 minus qr xr. So this is the Fourier integral, the inverse Fourier integral. Inside the integrand, what we have is Klein-Gordon operator y1 plus n squared y and y. Ooh, sorry. So this is y. So this should be y. Yeah, sorry. This should be y. plus m square, triangle operator, and then x1 plus triangle operator by xr plus m square times that acts on the correlation function. Time order phi 1 by yn by x1 by xn r and then omega. So this correlation triangle operator acts on. So each time, oh, you should tell me. Sorry. Why I make such a stupid mistake? Sorry. You should point it out. You have a phi 1 1. Okay. This is a mistake I made. Okay, maybe I should write down a bit more precisely. E2 out by y1 dp1. Okay, yeah. Q1. Okay. So each time what we need to do is the insert operator and act on triangle operator to get rid of this P1 here. You have to do the same thing. You just repeat. If you try to get rid of P2 here, what we need to do is insert triangle operator and phi 1 y2. That's what you need to do. The same thing happened here, Q1. To get rid of, unfortunately, here I omitted. So this is P1 out phi of x1 and P2 P. To get rid of P1, we insert phi of x1 and do the acts on the triangle operator, and then just do the inverse Fourier transformation. That's what we did. So we can do the sorry, Q2. So to get rid of Q1, yeah. So we just active phi of x1 and it acts on triangle operator, and this e to the minus sign. So this is called let's see, reduction formula. And let's what it means. To see what it means, let's go to the momentum space. To see what it means, we need to go to momentum space. So momentum space is that the this element in momentum space is a disconnected piece. Disconnect diagram plus I times C minus 1/2 n plus r product of p I plus m squared and minus I runs from 1 to n and the product of minus qi plus qm squared plus m squared, where let's go j maybe. J is equal to 1 to r, and that times the correlation function, time order correlation function. P1 total by Q1 total omega. Okay, that's what we have. So this is a momentum space representation of this matrix element. Okay. So therefore, if you do that inverse transformation, so this means that let me go to the inverse Fourier transformation. What we have is that the So this is a relation between time order correlation function and S matrix theory. So this is the relation between, this is S matrix, and this is time order correlation function. Time order correlation function. Okay. So this is a relation between S matrix element and the time order correlation function. And then they are related by this kind of propagator with the wave function renormalization. Okay. Okay, so what we have is that this, so if you do the image Fourier transformation, what we have is the schematically I d for yi and e to the I yi and the product of j d for xj e to the minus iqj xj and omega time order correction function is equal to product of I square minus m square I times square z and then j I qj square m square I times square z, and then you have p1 s matrix and q1 this is the point. So this is a relation between another way to see time order correlation function, inverse Fourier transformation time order correlation function, and this is S matrix element between Q1 and P1. Okay, so this is another way to see the LSC reduction formula. This means that the essential correlation function of this guy is equal to, schematically, you have this epoch, right, amputated, and then this is the so this is Q1 dot QR and P1 dot PN. And amputated means that you cannot separate. For instance, you cannot have this kind of diagram, whatever. I mean, it depends on the theory you consider. Here I consider scalar theory, so let's consider. Anyway, so okay, this is not amputated. This is not amputated, not because I mean they can separate, right? Do you understand what I mean? Do you have any comments or questions?
We call wasn't that taxing only certain one of stuff like that.
Oh,
But this time
no, amputated means that you cannot separate. It's really connected. Yeah. When you say amputated means the you cannot separate the diagram really. I hope I'm not mistaken. Yeah. You cannot separate the Yeah, so they really you have to be connected to here. You're connected here. You have to be connected to asymmetric element, which stands for this amputated one. And so this is not the case. I hope my English is not. Yeah, I think that's my understanding. Yeah. Correct me if I'm wrong. Okay. Yeah. So yeah. Anyway, so yeah. So this is not included. This is not included. And then here you have a quantum correction for propagator. This quantum correction propagator who stands for this one I times square z times p square minus m square. So this is propagator. Of course, then let me write down the by color. Red one. I think I'm running out of time. So yeah, this part stands for this one. This part. And then hopefully you can distinguish orange. This part is this guy. And then the middle part so that's the meaning of the this act. And just to give you a comment. So the reason why, so when you compute electron vertex function to the quantum correction electron vertex function, so we just consider this kind of diagram. Electron vertex function, we consider this is p and p prime, and I call it this is I forgot the p minus k and the k, and here p prime minus k and the q. So this is what we have considered an electron vertex function. But of course, if you consider one loop diagram, no one prohibits to consider this diagram. Okay. This is also one loop, right? But however, this can be treated as loop correction to electron propagator times this guy, the tree level one. Okay. Therefore, this is just a part we just consider here. Okay. So this will just change the Baire propagator to I times p square minus m square. Times the, of course, wave function renormalization up to square root of z. I mean, up to, depending on how you normalize. So this part, this correction, the part is really include this part. Okay. On the other hand, also you can just consider the following case. So this is just the same thing. So this one plus the correction to electron propagator here, like this. This part corresponds to really here. Okay. So therefore, once you change from Baire, it's an electron propagator. So maybe I should write down the following way: I times p slash minus m0 to I times d2 up to square root 2 to p slash minus m. So this is Baire mass to the ordinary physical mass. Okay. So this is once you change from the Baire propagator to the quantum corrected propagator, you don't need to include this this diagram. So only what matter is this guy. So this guy really corresponds to this blue guy. And then this one loop correction to the electron propagator really absorbed into the lag part. So therefore, what this LSZ tells us that once you consider the amplitude of the diagram, one has to be careful about the amputated guy, or like connected S matrix guy, and then lex guy, which is quantum corrected one. So that's what the LSC tells. And then anyway, that can be also used to derive it. I mean, that's like a very how to say, indirect way to show Z1 equal to Z2 in the Paskin's section 7.4, as far as I recall, to use the LSC. But I think word Takahashi is the best way to derive this one, so I just avoid it. But anyway, so LSC, by using it as LSC, one can also just argue that why Z1 should be equal to Z2, which is written in Paskin's book in section 7 point something. But I'm not gonna explain because I'm already showing by using the end of section 7.2. Okay, Paskin and Schroeder. If you're interested in section 7.2 at the end of, by using LC, they argue Z1 should be equal to Z2. Anyway. So that's another way to see by using LSC reduction form. Okay, so that's meaning of the LSC. The quantum correction really depends on the really connected diagram plus propagator. That's what this LSC tells us. And then I think the time is over. So the Paskin and Schroeder also talk about optical theorem in 7.3, and I have written the note for optical theorem, but I'm not gonna explain. If you're interested, you can just read, and if you have a question, you can privately ask me on a WeChat or office hour. And I hope you enjoy the QFT1. And then if you have a question, do you have a question? Okay, so then thank you very much. Okay, bye. Yeah. So anyway, so we'll see you in the next week for final exam. But don't be so scared. And then if you have a question about anything, just send me the message via WeChat, or we will see in office hour. Anyway.